guess everybody's sweating now, so I'm stopping anything now. For B. Now everybody voted? Okay. What was it? Translational and rotational, yes. Very good. They're a little tricky. So here's an application of a garage door. What do we have on the top of a garage door? Springs. Springs. Why? So it's easier to pull up, and if it's actually designed right, what's going to happen? As this goes up, the spring will unwind, wind. As it goes down, it's going to unwind. And so basically, as this goes up, you'll get energy stored in the spring. Other way around, yeah. Thank you. All right, here, you can have this all goes in. Basically, the energy you get, as this goes up, you'll get more potential energy. And so basically what you want is the potential energy lost in the spring to equal the potential energy gained in the door. And if that's the case, then basically the only force you need to apply is in the force to accelerate the door. You don't have any lifting force. And so that you can relate the torsional spring stiffness to the weight of the door so that everything matches up nicely. Similar concept here. Here we have a torsional spring. Do you know what a torsional spring is?
Not really, no.
Have you ever seen a clothespin?
Yeah. Yes.
No? Yes. Clothespin, no, you put our clothes in the dryer. Right? It has a spiral thingy on it, and as you twist it, the spiral thingy wants it to close back in. So that's a torsional spring. And so what's the purpose of this torsional spring on this car?
To hold the hood up.
It holds the hood up. Right, so as this lifts up, you get potential energy in that, so you want to lose the potential energy in your spring. That's how you would go about designing it. And here, oh look, here we have a linkage, and so we can have our kinematic equation. Right, to relate the position change.
No.
No, we could if we were designing it, but we're not going to be designing it in this course. But basically, that would be how they would design it. So you would have your kinematics, so then you can figure out what your height of your car hood is versus the angle between the two lengths. You develop an equation for that, and then you can basically figure out what your spring constant had to do with that. So we're going to talk about conservation of energy, and it's similar, which is why I jumped directly last class to conservation of energy with the modifier of the work lost, because springs are confusing. So how do we know we're going to use work energy or conservation of energy? Velocities, forces, and distances. So if we're looking for how fast we're going after a certain distance, probably we want to use work energy or conservation of energy if we have no friction. So work is a conservative force. Conservative, what's conservative? It means most Republican? No. In dynamics, a conservative force is independent of path. Doesn't matter how you stretch your spring. If your string has a certain stretch, it has a certain work to get it to stretch that far. You can push behind your back or whatever. Conservative force is independent of path, only on the initial and final positions. So gravity and elastic forces like springs are our true conservative forces. What's not conservative? Friction. And so you can add that friction force into your work energy. So you can do work energy in terms of potential plus kinetic plus non-conservative work equals potential plus kinetic. And then you can still think in terms of potential energy for springs, so you don't get confused with the work in springs. And then you can still deal with your non-conservative friction forces. So if we have no non-conservative, then we have T, which is kinetic, and V, which is potential. I don't know. I have no idea. Maybe it's French or something. I know, but the FE uses T and V, right? Yeah. So therefore, it would be good to see it before we take the FE exam. German. Probably makes perfect sense in German. But we don't speak German. So, bonus point. Anybody can explain why we have T and V? Google it during class.
Really?
So, basically, kinetic energy, you set a datum and MGH or WH. So, potential gravity MGH, just like before. And then springs, we have 1/2 KS squared. Question?
Yeah.
Whoa.
Sorry.
That was a dramatic question.
Sorry. Just so you know, FYI, the potential energy on the FE exam is actually U, not V.
Ooh.
Yeah, it's noted as U.
W for word.
So it gets even more confusing because.
All right, so we have to be trilingual.
T is kinetic energy, but U is potential.
U is potential. Thank you. For
Yeah, yeah.
It states it in the packet. It's not like
T and U. Right there.
T and U. Why? Because V is velocity.
They use U as energy.
that's their packet.
I don't know. So V is voltage. I don't know. Oh. Are you expecting? You are 24 in CPU. You looking for dynamics?
Yes.
Welcome. You made it.
Now
Now you're in the right class. Welcome. I'm Dr. Heckman. This is dynamics. It's a junior level mechanical civil course. It's a mechanical course that the civils have to take. Have a seat. So, we're talking about energy. So you might take this in a high school physics class, except for now we need. So basically, we can take our total V or U or V. It's the gravity and elastic, which is your spring, and KS squared. What happens if we have a rotational spring? What would the equation be? KS becomes
Omega.
no.
Theta.
V is omega. X is theta. So it's 1/2 K theta squared. It's not that hard. Translate, right? K becomes K, half becomes a half, S becomes theta. Kinetic energy, we have 1/2 mv squared of the center of gravity. For translation, rotation is 1/2 ig omega squared. So if we rotate and translate, we have both. What happens if we rotate about a single point? Say your Sharpie impact tester. It's IO omega squared. It would be a substitution. You can combine both of these terms into IO omega squared. And then you basically work energy. So here we have an example. We have two massless sliders to guide us. Massless. We could add mass, but that adds.
A and B are massless.
A and B are massless.
The rod.
The rod has mass. It used to be that A and B have mass, and the rod didn't have mass, because we didn't know how to deal with stuff that rotated. Now we're dealing with stuff that rotated. We have a mass of 10 kg, spring constant of 800 newtons per meter for our spring, and we're unstretched when theta is equal to 0, which makes our spring a lot easier. And so basically, that's our system. What's going to happen? If we drop 30 degrees, how fast are we going to be rotating? So, how do we know that this is a work energy problem? We're asking for a velocity and we're given an angle. And springs and gravity, so that also hints that we're talking about work energy.
Define velocity.
So, let's see if I can. A, B, M. So, basically, what is our equation? We have, what is our kinetic energy? kinetic energy is 1/2 mv squared plus 1/2 I omega squared. What is I for a rod?
So 1/12?
It's 1/12 ml squared. And you'll probably not need a formula sheet for this because you've been using it. So, how can we...
Is that rotating around the ends or is it in the middle?
So, this is... Where is it rotating about? About the instant center. Where is the instant center?
Down.
It's down. It's either up or down from A because it's perpendicular to the way A is going. And it's also perpendicular to the way B is going. So here is our instant center. So at this instant, this block is rotating about this point right there. This is 0.2 meters. This is also 0.2 meters. How far away are we from the instant center?
We are 0.2 meters.
This is also 0.2 meters. Right? It's similar triangles. So, what is our velocity? How can we relate our velocity to omega? D is equal to? R squared, no. R omega.
There's too many of these.
There's too many of these. So 0.2 meters times omega. This is a V of the CG. So this is the V of the CG, and this is I about G. So this is I about G. So therefore, our kinetic energy, plugging everything back in, it's 1/2 mass times 0.2 meters times omega. What's our mass? 10 kg. And that's our velocity at our center of gravity, and then we need to square that. That's 1/2 m BCG squared plus 1/2 ICG, which is 1/12 mass is 10 kg. What's L? The length of the rod, which in our case is 0.4 meters squared times omega squared. So this term here, oops, all the way up to here, is IG, and this term here is the G. When we substitute it in here, we substitute it in here. And so if everything works out well, oh, I didn't write it down. So that's your kinetic energy in terms of any position, or in terms of our last position. What's our initial, this is our final kinetic energy. What's our initial kinetic energy? 0. So 1, 2. Our initial kinetic energy is 0. So our final kinetic energy is equal to, well, what's our initial potential energy? Well, where do we want to set our datum?
Anywhere.
If we set our datum when theta is equal to 0, that's our height is equal to 0, then we have, well, our spring is unstretched when theta is equal to 0, so that's a good datum to think about. So no potential energy in our spring when theta is equal to 0. Let's set h is equal to 0 there as well. And so our initial 0 we'd look something like this. And so this is the point we say h equals 0. So black is now dead.
Yeah.
It's fading. Let's go blue. That would we do in Michigan, depending on All right, so what is our potential energy? It's equal to 1/2 kx squared plus mgh, or our weight times our height. What is x going to be? At our final condition, we are at 30 degrees. So this distance here is x.
That's 0.2.
0.4 sine theta.
No.
Is it 0.2?
What?
0.4 sine theta.
It's 1/2 of 0.4, isn't it?
Yes, 1/2 of, if this is 30 degrees, then it's x over 0.4 is sine 30. So x in our case, so it's equal to 1/2. Our k is 800 newtons per meter. X in our case is this, which is 0.4 times sine of 30 degrees, or 0.2
Squared.
squared.
Then what's H if that's not-
What is h?
0.4.
No,
Negative.
Well, it's negative.
no. H is h of what?
From the center of gravity.
H is the center of gravity height. So h is here. This is h.
0.2.
0.1.
It's half of the distance.
So it's half of that distance. So this is plus our mass, which is 10 kg. What do I do for g? Oh, shucks. I used my funny one. 9.81 meters per second squared times our h. 0.2 times sine of 30. And this is meters. And so if we set our potential energy plus our kinetic energy equal to 0,
H is going to be negative, right?
and h is negative, yes, thank you. We went down. So basically what we do is we set PE plus KE2 equals PE1 plus KE1. For both of these is equal to 0. And solve for omega, we can get that omega equals 4.82 radians per second. So we basically have this equals, this plus this equals 0. And the only unknown we have is omega squared. All right? We use the energy equation, yeah. All right, here we have something different. Now we have, what do we have here? We have a rod, 30 kg rod. Oh, good, we're still in the metric system.
Forget about
Right? What do we have? We're released from rest when theta is equal to 0. So we start off horizontally. This one doesn't work. And it's going to fall, oh, good, 30 degrees. Why do we like 30? Because sine theta is a half, and then at least half of our numbers are good. So we want to figure out the angular velocity of the rod when theta is equal to 30. We're released from rest. When theta is equal to 0, the spring is also stretched when theta is equal to 0. So similar concept when we're doing energy, except for now we're rotating about a fixed point, where here we were rotating about our instant center. But similar concept. And so initially, we start off like this. I probably should attach it to the roof. So this is initial. And then final is going to be down like this. at 30 degrees. And what do we have? Our springy Dewey. Where is our springy Dewey? So our springy Dewey is attached right here. And this is 1.5 meters. And this is 2 meters. Where's our springy Dewey here?
0.5 to the right.
So this is 1.5 meters, and this is 2 meters. So it's, yeah, it's 0.5 to the right. And this is,
Where it's unstretched.
our spring is unstretched right there. Interesting. Fascinating. All right. So drawing a picture does help. I initially didn't see that the spring has an initial, so basically the spring at L0 is equal to 0.5 meters. We are unstretched. That is, we have no energy inside of our spring. Okay, so what is our kinetic energy? It's equal to what? Well, initially it's 0 because we're at rest. So our final kinetic energy is 1/2 times what?
Mass.
Well,
IG.
it's 1/2 Ig, or we are rotating now about a fixed point. So we can just use I/O times omega squared. I/O, I/O. It's off to work, I go. What is I/O?
1/3.
It's 1/3 ml squared. So this is an advantage about using I/O because I/O is actually in your table. It's 1/3 ml squared. If I/O is not in your table, then you might as well use 1/2 mv squared plus 1/2 Ig, both of which are in your table. But I/O is in the table as well. And so we now know. And then omega, well, that's what we're trying to find. And that makes our life a little simpler.
So when there's a fixed point, we don't need the 1/2 mv squared.
Correct. You use the I about the fixed point. So we could, in this case, use I about our fixed point right here.
But we don't.
But that's not in the table. So therefore we went VG. This always works.
This is a special case.
That works for a fixed point at that instant. So that I/O works for an instant center, but here the instant center is moving around and it's complicated, and it's not in the table. So we would have to use the parallel axis theorem to find out what I/O is.
So that would come out the same though.
It would come out the same, yeah. It's
If you have
yeah.
a fixed point.
If you have a fixed point, I/O is in the table, and then you can just go for it. All right, so we have that. So that's our kinetic energy final. What's our potential energy final? Oh, we need to set a point where height is equal to 0. I like this, right? H equals 0. So what's the height here? Where is the height located?
0.75.
It's
Sine 30.
It's the height is at the center, so this is H2, which is equal to 0.75 times sine 30 degrees, which is 0.375 meters. All right, so we learned the secret from last time. The height is not at the end, the height is at the center of gravity. What's the stretch of the spring final?
It's 0.75 times.
Square root of 0.75
So
squared.
0. So you need to find the final.
Well, what is the final length of the spring?
Well, you know that
0.
you can find the.
Now, the length of the spring is not 0
Oh,
right
that
now.
final.
Right, what is L? How do we find the length of the spring?
Oh, the square root of 0.75 squared plus 0.5 squared. Oh,
It's the length divided by the cosine of
Right, so law of cosines.
Cosine.
So L2 squared equals 2 squared plus 1.5 squared minus 2 times 1.5 times 2 times cosine of 30 degrees. So this looks like a right angle, but it isn't. So then you have to use the law of cosines, and we do that. We get that L2 equals 1.027 meters. So what is the stretch of the spring to? It's L2 minus L0 is 0.527 meters. So what do we have? We have kinetic energy 1 plus potential energy 1 equals kinetic energy 2 plus potential energy 2 from gravity plus potential energy 2 from elasticity. This is 0. What's our final kinetic energy? It's 1/2 I0, so it's 1/3. A rod is 30 kg times omega squared. Wait, 1/2 mass L squared. Our length is 1.5 meters squared. So 1/2 I0 times omega squared plus potential energy 2 of gravity. What's that going to be? It's our mass times gravity. So its mass is 30 kg. Gravity is 9.81 meters per second squared. Our h is negative 0.375 meters. So this is mgh. That's gravity, and it's negative, which means we've gone down. Plus potential energy from our spring is 1/2. K is 80 newtons per meter times S squared 0.527 meters squared. And that's all equal to 0. So from that we can calculate that omega is equal to 2.97 radians per second. If we plug it into our calculator, or MATLAB, or Excel. All right. So what do we have here? At the instance shown, the spring is undeformed. Determine the change in potential energy if the 20 kilogram disc rolls 2 revolutions without slipping. No calculations involved.
So this drawing is where it's totally in rest, right?
Totally at rest there. Now roll. It's not at rest.
Well, I mean, it's not. This isn't where we're.
This is.
When you start.
This is where we're calling h
Initial.
equal to 0. Initial. Because we have initial velocity, the spring is going to stretch. And it's rolling down. Yeah, because we have the 3 meters per second velocity. Yeah. gravity going to come into play, and what are the signs? It's really right there. All right, another 10 seconds. Three, two, one. That's everybody. We didn't give quickers to the visiting students. Good. Looks like we got it right. Yay. Wait, is it right?
That's right.
Basically, C, the spring, this is the spring that says positive. Spring is, and then the spring is stretching, so it has positive potential. We're going down, which is negative for gravity. What's the kinetic energy at this instant?
Which is
After we've rolled so far down. No, at this instant right here. What? Sorry.
oh.
At the instant in the picture, not in the instant after.
So initially, what's the kinetic energy?
Yes.
Is this a trick question?
But it's not.
We're moving at 3 meters per second initially.
Oh, okay, I didn't see. Okay.
You didn't see that part. Just because these two problems started out not moving, now we're starting out at 3 meters per second. We're not sure how we got there. We might have started further up the hill, but now we're at 3 meters per second.
Still not slipping, right?
It's still not slipping. Yeah. Oh, I see typo.
What?
What? Where? B should be 3.
Oh yeah, because that's the length.
Yeah. All right.
What's the 10? That one.
Isn't it 0.5 the G?
No, this is 1/2. Where's my 1/2 mass R squared is IG.
But you got see, I think you got 1.5.
How do you gauge over there?
That's 0.5.
What?
Your kg
The coefficient
is
is
0.5.
And given information.
10 is the omega.
Oh, kg.
So, yeah.
Go back.
Ah, there's the sun.
Kg, that's the radius of gyration, right?
Yeah. All right. I was thinking.
Oh, and that takes the place of the.
All right, one more time. You was right.
This is the radius of gyration.
This 1/2. This is IG because kg is 0.5.
Yeah.
And the 10. How do we get 10?
It's V over R.
It's omega. It's V over R. Is 10. The right answer is. Everybody voted. Let's see, it's both. Because it's both rotating and translating. So the total energy is both. All right, now. What? We're going to break a pencil.
There's not 8 of these.
All right, so it says here we have 15 joules. So we have 15 joules of energy. At the initial angle is 161 degrees. So this is basically the potential energy difference between when it's up and when it's down. I should have safety glasses for those nearby.
Should we film this?
Oh, hey, we have a video camera even. Conveniently located.
Do you want me
Wait,
to hold it?
sure.
Jim needs to see it.
Yeah, Jim wants to see this.
Jim wants to. Jim. All right, so we're finally breaking
Maybe
the
the camera will
pencil.
protect you.
All right, so
Where's this?
Oh my goodness. It's
you got it. Ready? Uno, dos, tres. Yeah, wrong way.
Oh, yeah. Put your finger there.
wow.
No, thank you.
I didn't see it.
Well, it's on video. You can watch it on YouTube. So basically,
You
this.
fell down when you did that.
What?
You fell down when you did that.
Oh, it fell down.
Yeah.
It says. Well, we're having. So we didn't break a pencil.
You know what? That's scientific.
So that has a little bit of. Yeah. Maybe tighten some bolt there. But basically, how fast are we going to go when we whack the specimen, which is the pencil, and then if we ended up going such that we ended up at 90 degrees, that is, the thing was horizontal, how fast, or basically, what do we do from there? All right, we're running a little late, so I'll just work on this. Wait, what happened? I need to go to the board, not. No. Okay. These are long equations.
A little bit.
A little bit. All right, we'll do our best. Green is not our best.
Another green bit.
We have another green. All right, we're starting here at 161 degrees. We know that this is equal to 15 joules compared to compared to when it's straight down. So it says right here that there's 15 joules of energy if it ends up being straight down. So, how does that help us?
Does that mean it's at 15 joules at the bottom if you
At
have
the-
it that high?
Correct.
Okay.
So if we would draw it down here, right, the difference in whatever the center of gravity and the other center of gravity, what we have is this mgh equals 15 joules. Right? So that's equal to mgh. Well, what's that height? So we basically have that 15 joules is equal to mg. What's the h? Yeah, h. What is h going to be? Well, we're going to have a certain L to the center of gravity. And so it's mg L times what? It's 1 plus, what's this instance here?
Oh.
90 minus.
It's 180 minus 161, or it's minus cosine of 161 degrees.
Pretty much that L minus L cosine 161.
So it's L minus L cosine 161, right? If we were down here, right, the difference in height, if this is theta, is going to be 1 minus cosine theta. It keeps on working all the way around. So it's 1 minus cosine theta, and theta is equal to 161 degrees. Okay.
Is L the total length?
L is the length to the CG.
Oh, to the center of gravity.
Yeah, MGH, remember MGH, H is to the center of gravity. Now here we don't have a simple rod, we have a complicated structure. So the center of gravity is probably going to be maybe right here, I don't know.
Wait, would it be the same to do L plus L sine theta?
It's still cosine theta, right? Sine theta is this direction. Sine theta is horizontal. Right? Sine is opposite over this. Cosine is adjacent over that. So the height, the horizontal distance is sine. The vertical distance is cosine. So the change in height, we're saying this is h equals 0.
Oh. Oh, I get what you're saying.
Change in height is L minus L cosine theta.
Can't you use L plus L sine of 71? Like if you, from the point, right, from the midpoint?
70.
Because I get the same answer, 1 minus cosine of 161 and
horizontal.
plus sine of 71. Yeah.
Oh,
like
this
that.
is 71
71,
degrees?
yeah.
Yeah, then you could do that.
Okay.
That's the same answer. Okay, so how fast are, so this is generally what we're going to have. How fast are you going at the bottom? What? Well, we know we're 15 joules at the bottom. What is 15 joules? 15 joules is equal to 1/2 I-O omega squared. Is equal to what? 1/2, what's I-O? 0.3 kg meters squared times omega squared. Therefore, omega is square root of 15 joules over. Did I do something wrong? Times 2 over 0.3. And that's equal to what?
215 or 3.
215? I don't know. 15 divided by 3 is 50 times 2 is 100.
Yeah.
That's 10.
It's a square root of 100.
It's 10. Right.
Is 10. So obviously this is a book problem because the answers turn out so nicely. Reality is never quite that easy. So how fast are we going? What is the speed of the angle? V equals R omega is equal to 0.4 meters times 10, and that's 4 meters per second. So, how much energy did we lose? When we broke our pencil, right, after we swung, that's how fast we're going, and then we hit our pencil, we had a collision, so we have some impulse, and then we end up going horizontal.
It's the difference between 50 potential energy that we get by
Right, so what's the final potential energy?
mg.
So in the end, we have, our final potential energy is just mgl. This is equal to the final dE. What's mgl equal to? We can use this equation here, said mgl is equal to 15 over 1 minus cosine of 161 degrees. And that's equal to 7.71 joules plus 1. So our final, so basically lost is 15 joules minus 7.71 joules is 7.29 joules. All right, couple last questions, which are probably interested in what the answer is, although you don't have time to vote. What's going to have energy? We're releasing from rest. Potential energy, V, What has potential energy here? Each of the blocks has potential energy. What about the pulley? No, because it doesn't go up and down. So the answer is B, only the two blocks. Kinetic energy after we've rotated through 90 degrees is what? It's MGL. It's D. Kinetic energy is always 1/2 mv squared plus 1/2 Ig.
That's a wrap.
This is a very, very